Hi, it's Mrs. Murdock, and today I want to talk about inorganic versus organic. So these are terms that we use to describe molecules. And as it turns out, a lot of things we talk about in biology is chemical. We talk a lot about chemistry in biology. So being able to classify these two different terms kind of gives us a beginning point to start talking about all the molecules that are so important to living things. We're all just walking chemistry sets. And having an understanding of the difference between molecules or compounds that are inorganic versus the ones that are organic is going to help us to organize our information in our heads a little bit better. So by definition, inorganic versus organic, we're not talking about going to the grocery store and you have organic produce and the only reason it's called that is because they didn't use pesticides or hormones to enhance it. That's not what we're talking about here. Here we're talking about pure structure of the molecule and what's there and what isn't. So with inorganic molecules, well, first of all, there's no carbon, but maybe it's better to go from the definition of the organic molecule. So all organic molecules have one particular thing in common. They all have, oops, pen's not working. There we go. They all have carbon atoms attached to hydrogen atoms by covalent bonds. All organic molecules have this. They have at least one carbon attached to a hydrogen by a covalent bond. And inorganic molecules do not have that. So they have no carbon to hydrogen connections, right? These do have it, those don't have it. Okay, so now if we go towards examples of inorganic versus organic, and we just make a little T-chart. Okay, so let's talk about water. We know water is a really, really important molecule for life. We talked about that in a different video. That would go on the inorganic side. So we have H2O, and the structure of it is here we have the hydrogen atoms connected to the oxygen by covalent bonds, and you don't have any carbon, and it's definitely inorganic. Another good example of an inorganic compound that's still also important to life would be table salt, NaCl. So salts are also inorganic. They're a little bit different than a molecule like water because a salt is bonded not by the covalent bonds that you see here. These are covalent bonds connecting the hydrogens to the oxygen. With sodium chloride, you have ionic bonds. So very quickly what you have, it's a little bit different. You have ions that keep their charge that are connected to other ions by ionic attractions that are actually very strong. So if you had a salt crystal, what you really have is a lattice, a crystalline lattice that I'm just drawing one little cube of it, but it would go on for quite a while, this crystalline lattice. And it would consist of all of these ions that retain their charges that are ionically connected together. And it would, you could go out and up and out and up. If you had one little salt particle that you were dissolving as a solute, for example, in a beaker of water, water is your solvent, you have an inorganic mixture. You have an inorganic mixture of water as a solvent with salt, sodium and chlorine ions dissolved in it, right? Okay, so there's two good examples of inorganic. So now here's the question. Carbon dioxide, right? CO2. Which is it? Is that an inorganic molecule or is it an organic molecule? If you said inorganic, you are correct. Carbon dioxide, it does have carbon. So your mind is probably saying, wait a minute, doesn't that mean it's organic? But it's not enough. You can't just have carbon to be considered organic. You also must have the bond to hydrogen. And carbon dioxide, if you look, has a double bond to oxygen on one side and another double bond to oxygen on the other side. There's no hydrogen here, no covalent bonds to hydrogen, and therefore carbon dioxide is considered an inorganic form of carbon. It's an inorganic form of carbon. It is gaseous. It's in our atmosphere. It is incredibly important to life, Plants use it as their carbon source to incorporate carbon into sugars. They get their carbon from the air, bring it in through their leaves and incorporate carbon into sugars using carbon dioxide. So it is important. It's part of the carbon cycle. It's part of the whole respiration photosynthetic cycle on the earth, but it's not organic. None of these three molecules here are bodybuilders. And what I mean by that is they're not very good at building muscles or building bone or building tissues or doing anything like that. They're still important to the maintenance of those tissues, but they are not, you can't just take, salt or carbon dioxide and build anything with it. So for that, you need organic molecules. And the reason organic molecules are so useful in the buildings of structures and cells and membranes and things like that is because of the carbon atom. The nature of the carbon atom is that it's very good at creating skeletons of itself. You can build lots of things with carbon. So let's start with a really small one. The most simple organic molecule that you can probably think of would be methane. Definitely not something that could build bodies. But you see that it is organic because look at the carbon to hydrogen bonds in methane gas. So there's a nice good example of a very tiny but organic molecule. And then you can also see how easy it would be to build skeletons using carbon, because carbon is able to not just attach to hydrogens, which are dead ends, you can't attach anything else to the other side of this hydrogen, but carbon can form chains of itself. It can form rings of itself because it can form these four covalent bonds at its four corners like that, because it has those electrons that are ready to bind to four other substances. It makes a good skeleton. So some of the examples of organic molecules that are useful and that build successfully. I'm also going to say with a slightly larger molecule, I'm going to stick with glucose because I like the way glucose shows a bit of chemistry of carbon. You know that glucose's formula is C6H12O6. So glucose, if I draw each atom and each bond, it looks like this. Glucose is a hexagon. So here's a carbon. It has an oxygen as part of the linchpin of its hexagon, but all the other corners of the hexagon are made of carbons. So this is an example of an organic molecule that incorporates its carbons into a ring like this and builds a skeleton for the other atoms to hook onto. Now you may notice that because I put an oxygen here, there's only 5 carbons in this ring so far. So what happened to the other 6th one? It's up here like that. Okay. So then the next thing is, where's the hydrogen? Where is the hydrogen bound here? Well, there's hydrogens where in lots of places. There's one here. There's one here. There's one here. One here. One here. And there's 2 up here. There. So lots of carbon to hydrogen bonds. That requirement is checked off. All right. What about the 6 oxygens though? We don't have all the hydrogen in there yet. Okay. So the oxygens are part of hydroxyl groups that kind of fill in the last places on the carbons, because every carbon has to have 4 covalent bonds coming out of it. So there's where those other oxygens went. There. Okay, so let's make sure I've done this right. We have 6 carbons. We have 6 oxygens. 1, 2, 3, 4, 5, 6. And we should have 12 hydrogens if you count them all, if I did this right. Okay, so that's how glucose is put together, and that's an example of a carbon skeleton working for organic. Okay, so going on from that, I'm not going to do a whole thing on carbohydrates here, but I wanted to point out that the other really important organic molecules that we put into this group include the larger biomolecules. So you can take a small biomolecule like glucose and hook it to other glucoses and make a big biomolecule, and that's called a macromolecule. So a lot of those macromolecules depend again on carbon's ability to make that carbon skeleton to hook onto itself, or make rings and make lines and make large molecules that can then be incorporated. So there are 4 important organic molecule categories. And they include the carbohydrates, like the one I exemplified above. They include proteins such as actin and myosin that are part of your muscles, proteins like hemoglobin, which is an oxygen transporter in your bloodstream, and there's all kinds of other types of proteins. One of the biggest building molecules in your body is proteins. Also, we have lipids, which are also very important. Long chains of carbons, like fats have those long chains, and they're hydrocarbons, and they store a lot of energy, and they also offer padding and insulation to animals. And finally, nucleic acids, which again depend on that skeleton of carbons and hydrogens, and include really important molecules for life like DNA. So that is a synopsis of organic versus inorganic, and I hope that was helpful.